Black holes are the most extreme objects in our universe. They're regions where gravity has become so powerful that nothing, not even light, can escape. Scientists have detected dozens of these cosmic monsters, and we've even captured images of their glowing surroundings. But here's a thought experiment that physicists have pondered for decades. What would actually happen to you, to your body and your experience of time itself, if you fell into one? The answer reveals some of the strangest predictions in all of modern physics. The first critical boundary you'd encounter is called the event horizon. This is the invisible sphere surrounding a black hole beyond which escape becomes impossible. Think of it as a one-way membrane in space itself. The size of this boundary depends on the black hole's mass. For a black hole with the mass of our Sun, the event horizon would be about 3 kilometers across. For a supermassive black hole millions of times heavier, it could span millions of kilometers. Surprisingly, as you approached this boundary, you might not notice anything special at first. As you fell closer, something remarkable would happen to time itself. This phenomenon is called gravitational time dilation. According to Einstein's general relativity, time passes more slowly in stronger gravitational fields. Near a black hole, this effect becomes extreme. Your watch would tick normally from your perspective, but to someone watching from a safe distance far away, your clock would appear to slow down dramatically. The closer you got to the event horizon, the more time would seem to stretch from their viewpoint. This isn't an illusion, it's a fundamental property of space-time near intense gravity. From the perspective of an outside observer watching you fall, something eerie would occur. They would never actually see you cross the event horizon. As you approached it, the light reflecting off your body would become increasingly redshifted, meaning stretched to longer, redder wavelengths. You would appear to move slower and slower, gradually fading from view as your image dimmed and reddened. To them, you would seem frozen at the edge of the black hole forever, your image slowly vanishing into darkness. But this is only what they see. Your experience would be completely different. From your own perspective, falling into the black hole, time would continue normally. You would cross the event horizon in a finite amount of your personal time. For a supermassive black hole, this crossing might feel unremarkable at first. The space around you would look increasingly distorted. Light from the outside universe would appear compressed into a shrinking circle behind you, while ahead, darkness would dominate. You'd be falling faster and faster, accelerating toward the center. Once past the event horizon, your fate would be sealed. Every possible path through space-time would lead inward toward the singularity at the center. Now we reach the most visceral prediction, spaghettification. This describes what tidal forces would do to your body. Tidal forces arise because gravity gets stronger the closer you are to a massive object. Your feet, being closer to the black hole center than your head, would experience stronger gravitational pull. This difference would stretch you vertically while compressing you horizontally. For a stellar mass black hole, these forces would become lethal long before you reached the event horizon, literally pulling you apart at the molecular level. The term spaghettification perfectly captures this grotesque stretching into a long, thin strand. Interestingly, the size of the black hole determines when spaghettification would kill you. For a small, stellar mass black hole, tidal forces would tear you apart while you were still far outside the event horizon. You'd die before the really strange physics began. But for a supermassive black hole, millions or billions of times the mass of our Sun, the tidal forces at the event horizon would be much gentler. You could actually cross the horizon intact and alive, experiencing the bizarre physics beyond. Of course, you'd still be doomed. The tidal forces would eventually destroy you deeper inside. At the very center of a black hole lies the singularity, a point where our current physics breaks down completely. According to general relativity, all the black hole's mass is compressed into an infinitely small, infinitely dense point. But most physicists believe this prediction signals that our theory is incomplete. We lack a working theory of quantum gravity that could describe what really happens at such extreme scales. The singularity represents the boundary of human knowledge. It's a place where the mathematics we use to describe the universe simply stops making sense. What truly exists there remains one of physics' deepest mysteries. Despite decades of theoretical work, fundamental questions remain. What happens to information that falls into a black hole? Does it disappear forever, or is it somehow preserved? This information paradox has troubled physicists since Stephen Hawking's work in the 1970s. Some theories suggest black holes might be connected to other regions of spacetime through wormholes, though there's no evidence for this. Others propose that what happens inside depends on quantum effects we don't yet fully understand. Until we develop a complete theory unifying gravity and quantum mechanics, the full truth of what happens inside a black hole will remain beyond our grasp, a cosmic secret kept by nature itself.